Good morning, students. Today we will start chapter 4, magnetic effects of current, and today is lecture 1. So start with this. Okay, so first of all, what we need to understand that electric current has magnetic effect. Who came up with this concept? Yes, Ørsted. So we will talk about that. Few things you must have done in your 10th class. Basic idea of how current carrying conductor produces magnetic effect. Current carrying conductor has magnetic effect. Okay, you can see here that if on this plate, right, iron fillings were kept, okay, and in that, now current was flowing through this wire. It is done in this manner. It is basically here there is some hole and this is the structure, right? On this plate, on this sheet, iron fillings were placed, and when current is made to pass through this wire, these iron fillings had this sort of structure. They aligned themselves in this circular pattern, right? Closer to this were more number of iron fillings. That gives the idea that closer to this conducting wire, field is strong. Magnetic effect is strongly felt closer to this wire, right? One thing. Second thing is that when we reverse the direction of current, if we place compass here, right, in one way, if direction is there, then compass will align themselves in some direction, and if we reverse the direction of current, it is in the another direction. That means compass align themselves in opposite direction. If current is reversed, direction of current is reversed. Okay, that was the basic experiment to show that magnetic effect is produced around a current carrying wire, current carrying conductor. So that is the simple idea behind this concept, Ørsted experiment. Okay, so first of all, chapter overview. Let us understand what all topics we are going to discuss in this chapter. And first is introduction, then Biot Savaart Law. Although it is written in this manner, we pronounce it as Biot Savaart Law. In this we have understood, okay, there would be magnetic field around a current carrying conductor. This law tells us what would be the magnetic field, what would be the magnitude and direction of magnetic field, right? Third is Ampere's circuital law. There is another law to measure magnetic field. There is some fundamental difference between the two. This one can be considered as very fundamental, right? Due to current element, small current element, we have the basic concept, and Ampere's circuital law also gives us the magnitude and direction of magnetic field. There is another law which gives us the magnetic field, which gives us the magnitude and direction of magnetic field. Okay, so in this chapter there are only two laws. this Biot Savaart law and Ampere circuital law, right? With the help of this, we will be able to find out the magnetic field due to solenoid, due to toroid, right? Due to the magnetic field in this particular, let's say, this cylindrical wire and multiple wire, right? Multiple wire. So this has got larger significance. We'll talk about this. Okay, next is magnetic force. We will find out what is the magnetic force experienced by a charged particle when it enters a magnetic field region, right? One thing. Second thing, two current carrying conductors also will experience force due to the field of one another. That is also there in this segment, magnetic force. Okay, next is cyclotron, right? Based on this magnetic force, there is cyclotron, which is used to accelerate a charged particle to high energy. This is very important instrument, okay, cyclotron. Then there is moving coil galvanometer. For moving coil galvanometer, we have to understand what is the torque on a current carrying coil. You know that moving coil galvanometer detects the presence of current, right? So these things are there in this particular chapter. So are you excited? Now let us understand what is this. Let us introduce the chapter in this. Moreover, we have done few things. Okay. Oersted actually noticed that a current in a straight conducting wire caused a noticeable deflection in a nearby magnetic compass needle, right? That gave the idea, that started the chapter actually start from that particular observation, right? Magnetic effect of current. A current carrying conductor has some magnetic effect. How do we say that magnetic effect is there? If magnetic compass needle is placed nearby, then there is a deflection in the compass. That means there must be some magnetic force, right? And we call that region in which that magnetic force can be felt, can be observed, magnetic effects can be observed, is called magnetic field. So let us understand what is magnetic field. Okay, one thing, changing the direction of flow of current caused the deflection in different direction. That is also a very important point. Okay, now what is magnetic field? The very basic idea. What is magnetic field? This we can easily define in this manner. Space around the conductor in which magnetic effect is observed is called magnetic field. This is very simple, right? We have some other way to define magnetic field, but that we will come to know when we have got some other parameter. Like I talked about magnetic force, in the chapter overview, we talked about that. When we will get to know what is that force, how to find out that force on a moving charged particle when it is entering in a magnetic field region, in that particular equation, there is another way to define magnetic field. So we will talk about that when we will do that particular topic. Okay. So right now, just a basic understanding of what is it. This is very simple. Space around the conductor in which magnetic effect is observed is called magnetic field. This is very simple definition you must have done in chapter, in class 10th. In class 10th, yes. Okay. Now, what is the unit of magnetic field? Tesla. Unit of magnetic field, SI unit of magnetic field is Tesla. And one more thing, 1 Tesla equals 10 raised to power 4 Gauss. Right? 1 Tesla equals 10 raised to power 4 Gauss. Gauss is the CGS unit of magnetic field. Gauss, right? Okay, now BS law, that is Biot Savaart Law. From here onwards, this chapter actually starts. We got to know what is magnetic field. We had the basic idea now, right? We have now the basic idea of magnetic field. Now we will figure out what is the direction and magnitude of magnetic field around a current carrying wire. From here onwards, we need to be very careful because we need to think in terms of 3D. Yes, 3D. I want you to just hold your hand like this, your left hand. That will give you the sense of axis. If you place it like this, try to understand, hold your left hand like this. This is x-axis, this is y-axis, this is z-axis. So basically this, when it is placed in this manner, this is x-axis, y-axis, and this is z-axis. Why 3D picture is required? You will come to know about it very soon. You will come to know about it. Okay, one thing, before we move ahead with this topic, I want you to recall the basics of cross product, because this chapter requires the concept of cross product. We have to understand, although there are few laws, Fleming's left hand rule, there is another tool to find out the force, the movement of charge, and magnetic field. There are three different entities and how they are particularly placed in a space, 3D space, right? But we need to be very clear about this, cross product. Cross product is required because at times when you are given questions based on this particular chapter, we have been given that in vector terms, all the parameters in vector terms. That means if we have that clear-cut idea, if we have enough practice of cross product, in this chapter we can move with confidence, right? Okay, so let us understand what is the basic idea behind this law. This law is very simple. As I told you, this is the fundamental law in this particular chapter, very fundamental law. This simply says that three things you have to understand. Three things. First is ideal. What is this ideal? Ideal is the element of what? What element? Length element. Length, basically. If this is a conducting wire, this small portion you can see here is dl. Right? Then you have current. So usually we call this ideal. We call this ideal to be current element. Current element. The segment of the wire in which current is flowing. The wire may have different turn in this, like this, okay? At different point, direction of current would be different. So suppose this segment we are taking, this segment, this particular segment. So this is DL and this I is flowing in this direction at this point, at this segment, the very small element. So ideal we need to take into account, okay? Ideal. So we'll call this current element. So this we need to keep in mind, okay? Now, another thing. There is sine theta. So what is this theta here? Just understand. There is a point where we need to find out the magnetic field. There is a point from this current carrying conductor. We need to find out magnetic field at that particular point, which is r distance apart from this particular segment, okay, r distance apart. So this also has some sense of direction, okay. So basically this theta is the angle, theta is the angle between ideal. This is also considered as vector. Mind it. This is also considered as vector. Although current is not a vector, this length also is not a vector, but in order to find out magnetic field, we consider this ideal element to be a vector, and this distance also a vector. So this also has some sense of direction, right? So this is very important to note here, right? So sine theta, this magnetic field, this law states that magnetic field due to current element is directly proportional to current element and directly proportional to sine theta and inversely proportional to square of the distance of the point. Distance of what? Of the point from the current element. Which point? The point where magnetic field is calculated. Yeah, this is very simple. So if you combine these three, the equation will be this. Now, there is a constant of proportionality. This constant of proportionality here, mu naught by 4 pi. Here mu naught is some factor which is depending upon the medium, right? The medium or the material basically. So that has got some significance. We will talk about this in the next chapter. Right now just understand that this is called, mu naught is called permeability of free space. Permeability of free space. And this mu naught is some constant value. Mu naught has some value that also we will understand. Mu naught equals 4 pi into 10 raised to power minus 7. Okay, 10 raised to power minus 7. Mind it. What is going to be the direction of SI unit of this permeability, right? Mind it, what is the direction? This is Tesla. Okay, this is Tesla. This is meter square. This also has got meter. So meter square, meter by meter square. That means this becomes meter. So Tesla meter per ampere. Sin theta has no unit. So what is the SI unit of this? Tesla meter per ampere. Tesla meter per ampere. Right. So this is the basic idea behind this. So final result in this is very simple. dB equals what? dB equals mu naught by 4 pi into I dl sine theta by r square. This is the constant of proportionality. And now three things: ideal, sine theta and r. Right? This is going to be a very simple formula. And if you closely look at it, it is very similar to what we did in electrostatics. Very similar to that. Close to that. Electric field is inversely proportional to square of that. Square of what? Square of the distance. Right? Distance where electric field is felt. One thing. Second thing, there we had due to the charge. Here what we are going to get, current into length. Right? Current into length. Sin theta has some significance. We'll talk about this soon. But dimensionally, if you speak, ideal, okay, ideal has got some significance here due to magnetic field, right? So due to this current element, magnetic field is required to be found. So it boils down to very simple thing. dB is inversely proportional to r square, directly proportional to ideal, and yes, sin theta is also there. We'll talk about this sin theta, why it is coming. Okay, as I have told you that in this particular chapter, we require concept of vector product. We require concept of vector product. Why this tool is very important? You know that vector product means cross product gives you one vector, another vector. So here this can be treated as what? Magnetic field can be treated as the product of two vectors, ideal, product of these two vectors, ideal and r. So if you wish to express magnetic field in terms of a vector, how this comes? Just try to understand. Ideal cross r vector, right? Now, this would become r cube. Here it would be r cube. And that too, let me put it in more specific way. This is vector r, mod of this and square cube of this basically. Okay. So this is magnetic field due to current element. BS law in vector form. BS law in vector form. Vector form. Right? So just ask yourself, what is happening? The cross product means, if you remember, what is it? This is mu naught by 4 pi, the constant of proportionality. I have taken it here. Okay. Now ideal cross theta. So ideal r sin theta. You are aware of this. A cross B is what? A cross B equals A B sin theta. Right? A B sin theta. Since it is a vector, so the direction of vector would be n cap here, and that is the vector which is perpendicular to these two vectors. We are aware of that. That's why I told you in this particular chapter, this concept of cross product is required. I would advise, if there is some difficulty in understanding that, go and first learn that, practice it enough, then things will get easier for you. Although I will talk about this, I will not leave you, as it is. I will, even if you are not aware of this, there is some difficulty in recalling, I will talk about this, okay, briefly. But in detail, if you have to master this cross product, go back to that, 11th topic, 11th chapter, 11th topic, when vectors are there, all vector algebra. Okay, do that. Okay, now what is left? This divided by r cube. So that is why finally we are getting it in this manner. Mu naught by 4 pi I dl sine theta by r square. So this is our magnitude. Understood? So this was the law. So this we need to understand. Right? Sine theta is coming. This is a vector. That means it is a cross product of two vectors. Okay, which two vectors? Ideal and r, cross product of ideal and r. Keep note of it. This sequence is important. It's not r cross ideal. It is ideal cross r. Okay, that thing. Now, you are saying that this is a vector product of two vectors, ideal cross r. All right. But if you wish to find out the direction of magnetic field, what is it going to be? So magnetic field is directed perpendicular to these two vectors as per the concept of cross product. Cross product or vector product. Right? Cross product or vector product. This we need to understand. So direction of magnetic field is perpendicular to these two vectors. Direction of magnetic field is perpendicular to the plane of ideal and r. Right? That's why I told you, if you remember, I had told you in the beginning itself that this is one plane, xy plane I'm taking, my palm is on the xy plane, right? And the z-axis is along this. So if you are taking it, if the palm is turned like this, anti-clockwise, direction is upward, right? So this direction is determined by right hand screw rule. What? Right hand thumb rule or right hand thumb rule or screw rule. Direction. Right? Direction of this magnetic field is determined by right hand thumb rule. How it is going to be? Just hold your right hand, okay? Curl your finger. Notice the direction of thumb. Direction of thumb is in this direction, right? In this way it is done when you are curling it like this. That means if anti-clockwise you are doing, if current is flowing anti-clockwise, this thumb will show the direction of magnetic field. The opposite is also true. But you need to do it vice versa. That means if direction of current is represented by the direction of thumb, then curl of the finger will give you the direction of magnetic field. If you reverse it, it is like this. Curl of the finger is clockwise and curl of the finger represents the direction of current. If you are taking that as direction of current, then thumb will show downward. Here in this chapter, we need to express things in 3D. In 3D, but we need to visualize it, but expressing it, obviously we have this 2D system, no? So we have some mechanism, some tool. So let us talk about this. In this particular chapter, this board you can see, this is the page, right? Or plane, whatever you say. If you are interested in showing up the direction of magnetic field or direction of current perpendicular to this page, but perpendicular to this page can be in two ways, into the page or out of the page. So this is into the page. into the page or plane, right? And this is considered as out of the page. Out of page. So in this particular chapter, this notation is very important. We have to visualize it in 3D terms, but while expressing, we have only 2D system, no? So we can do it in this manner. Into the page, cross, out of the page, outward, right? Out of the page is dot. Understood? So this we need to understand. So let us talk about this direction. If current is in this direction, so let us take this example. If this direction, thumb is representing the direction of current, then this will, the curl of the finger in this direction, here will show the direction, direction of magnetic field. So here in this side it is out of the page, this side it is into the page. The thumb and this curl system is placed in this manner. Thumb is in the XY plane, this is XY plane, suppose this is XY plane. Perpendicular to this, curl of the finger, and it goes like this, it is coming out and getting into this. So this is the direction of magnetic field. Direction of magnetic field. Okay, if the direction of current is reversed, like this, so this is into the page, the curl of the finger will show us the direction of magnetic field. So this is into the page. If direction of current is reversed, then this is into the page. And this is out of the page. Okay? So this we need to understand if this is the direction of current. One more thing. If you have clockwise direction of current, clockwise direction of current, then what would be the magnetic field? Magnetic field would be outward, inward. Magnetic field will be inward. If you have clockwise current, magnetic field will be inward. As you know that inward magnetic field means south polarity. Just put it. You see that this is anti-clockwise in this, this is clockwise, right? This is clockwise showing up. So magnetic field, when current is clockwise, magnetic field will be inward, and that can also be considered as south polarity. Similarly, anti-clockwise current is this. So in this way, anti-clockwise current, if curl of the finger is showing the direction of current, then magnetic field will be upward. So you are aware of that. You must have done it in class 10th. From north polarity, magnetic field lines start. So if it is upward like this, so we can consider it as north polarity, right? So north polarity. This can be considered as this. If current is this, so this is into the page. Magnetic field is into the page. If current is anti-clockwise, then it is out of the page. Magnetic field will be, this is B. This is B, magnetic field out of the page. And this, in terms of polarity also, we can do this. This is north polarity, this is south polarity. This one is south polarity, this one is north polarity. If anti-clockwise current, then north polarity. Clockwise current, south polarity. These things are quite important. Okay? While finding out the direction of magnetic field, we need to be very, very careful about this. How the direction of magnetic field is determined? Yes, right hand thumb rule. Right hand thumb rule. Okay. So this is the end of the session now. We will do all the other derivations and further stuff in the next session.